Hi, my name is Nathan. I'm an 11th grader, and this is my research project discovering a novel irreversible structural phase transition in phosphorene and discussing the material anisotropy of phosphorene under high deformation. As an introduction, phosphorene belongs to an emerging class of 2D materials that may dramatically change the way electronics perform under extreme conditions. Because of phosphorene's unique puckered structure, it has many incredible properties, resulting in many applications of phosphorene in biomedics, electronics, and optics. However, despite its emerging popularity in research, it remains a challenge how phosphorene behaves mechanically, electronically, and optically when loaded along an arbitrary crystallographic direction. Investigating this anisotropy is a major goal of this research. Additionally, in this research, we hope to enable the design and discovery of new electronic devices with unprecedented electronic and optical functions under extreme loading conditions. For example, investigation of materials under extreme loading conditions allows for the future possibility of flexible devices. Imagine being able to wrap your phone around your arm for easy carrying if you weren't wearing any pockets. So we asked these research questions. How does uniaxial deformation at the different chiral angles affect the material properties of phosphorene differently? And what are unexpected properties of phosphorene under extreme loading conditions? We answer these questions by simulating strain application on phosphorene using density functional theory simulations. From our simulations, we observe a novel structural phase transition. In such, the material reorients from the 9-degree zigzag case into the 0-degree armchair case. This phase transition is specific to when strain is applied to the 90-degree case, occurring only when the strain level is at 31 degrees, as shown within these figures. The reorientation is also observable through a drastic change of material properties. Most notably, as shown, we see a dip in stress and elastic energies during the phase transition, meaning the material resists initial fracture and then can sustain more strain. However, what motivates this phase transition? You can analyze the conjugate gradient relaxation steps during the phase transition to see how the material relaxes into its new 0-degree structure. In general, we see that the transition is motivated by bond instability, and the transition occurs to stabilize the phosphine layer. Apart from the phase transition, we can analyze the anisotropy of phosphine layers. Here, we generally see that the higher chirality results in higher bond length. Additionally, angle and strength are logistically correlated, whereas stiffness is chirality independent. Analyzing orbital occupancies, we see that higher angle results in quicker 3s orbital occupancy, quicker 3px orbital removal, and greater overall 3pz occupancy increase. Notice the drastic changes in orbital occupancies during the phase transitions as well. Finally, analyzing electronic structures, we see general trends where higher strain results in lower band gaps and higher angle results to quicker decaying band gaps. Additionally, we see that within the phase transition, there is a large band gap regeneration due to the material relaxation. This research has many applications. For example, within the structural phase transition, its stress reduction prior to fracture can mean future self-repairing fracture-resistant materials. Additionally, the band gap regeneration would allow for future strain-stimulated or optical switches. There are many possibilities for future studies as well, where we can explore other puckered materials, phosphorene derivatives, and other material changes due to the phase transition. To conclude, in our research, we discover a novel phase transition from high strain application in phosphorene zigzag direction motivated by bond instability, resulting in significant changes in material properties. Additionally, we analyzed the anisotropic properties of phosphorene by discussing how strain at different angles affects orbital occupancies, material strengths and stiffnesses, bond strains, and electronic structures differently. Thanks for listening to my presentation. Here are my most important references, and not to mention, special thanks to my research mentor and sponsor.